This presentation is delivered by the Stanford Center for Professional Development.
Okay, hi, I'm back to continue reverting back to statistical parsing. Right, so last time Dan Jarafsky talked about semantic role labeling. I mean, I think for many people, the idea of semantic role labeling is directly answering the kind of who did what to whom question, which is sort of the essence of having a kind of a rough relational meaning taken out of sentences. That's something that I'm not sure if he mentioned, is there actually has been work done in some of these Connell evaluations as to, well, can you get at that representation successfully without doing syntactic parsing? And the answer to that seems to be a fairly large no, so that for the kind of shared task evaluations of semantic role labeling that were done at Connell for 2 successive years, that for 1 year they've imposed this constraint that you were not allowed to work with full parsers, that you're allowed to use part of speech information, partial chunking to get base noun phrases and various low-level kind of information, but you could not use full syntactic structures. And the results from that were just a lot worse than the results that people could get for doing semantic role labeling using syntactic structures. Now, I'm personally a fan of parsing, so I'm not completely unbiased, but I would argue that there's pretty strong evidence from that kind of evaluation that building syntactic structures is just a very effective means of working out the macro structure of the sentence, and that fits with how parsing has normally been motivated as essentially a prerequisite that you have to do before you can do deeper level meaning extraction from sentences. And the nice thing is that now that there are these quite available, effective, reasonable speed statistical parsers widely available, I think that you're starting to see more and more results of people both inside NLP and people outside NLP and just political science or whatever that want to try and get meaning relationships out of sentences, successfully exploiting syntactic parsers to have it work better. Okay, so reverting back to statistical parsing, what I want to do today is first of all talk about this idea of lexicalized parsers, which has been one of the key ideas that have been pursued in terms of improving statistical parsing. And then I'm going to go on and say a bit more about ways that you can go about parsing, which is effectively solving the search problem of parsing. And then next Monday I'll do the final lecture on parsing, and in that one I'll probably still be finishing off the parsing search techniques, and then I'll talk some about dependency parsing, and then just a little bit about discriminative methods in parsing and why they're useful. Okay, so I kind of just mentioned the idea of lexicalization before, but the idea was this, that if you just know that you had a verb phrase with a verb and a prepositional phrase, yeah, that's kind of grammatically well formed to build that structure, but it tells you nothing at all about whether that's a reasonable structure to build, that you have none of the lexicalization that you had in the purely linear bigram or trigram model, which told you, is this a reasonable sequence of words, the kind of thing people say. And so the idea was, well, can't we just capture that pretty well in a PCFG model if we say that for any phrase, it can be fairly well represented in its meaning by its head word. So a noun is the head of a noun phrase, the verb is the head of a verb phrase in the sentence. And so we kind of percolate these heads up. And so we now have this enormous space of non-terminals which include a lexical head. And well then, as soon as we do that, we then have a verb phrase walked, rewriting as a prepositional phrase into, and you can say, well, walked into, that's a perfectly reasonable pair. And we have a PP into with a child of a noun phrase store, into store, that sounds reasonable. Whereas if the sentence had been something like, Sue walked onto the store, you'd say, onto the store. That's kind of a little bit weird there. We want to just prefer that kind of structure being built. Okay. And in particular, in the first lecture on parsing, I talked quite a bit about this notion of lexicalization and attachment dependencies for prepositional phrases. And we can see how some of that is being captured as soon as we lexicalize these parsers. So announce rates for January. We've now got this bilexical probability between rates and for, and we have rates for January seems kind of reasonable. And here we have announce rates in January, so then we have announce in. And so the argument is announce in sounds fairly likely, whereas announce for sounds not impossible but less common. Conversely, rates for sounds very natural, but rates in doesn't sound so good. So we're capturing some of the information that seemed important for doing prepositional phrase attachment. But we're not actually capturing all of it. So what information are we not capturing that is probably useful? I think so the thing that we're not capturing is what's the role of the head of the noun phrase inside the prepositional phrase, which is January. But there's also a lot of information for doing prepositional phrase attachments, for also looking at rates January, whether that's plausible, versus announce January. So here we've got announce January in this example, they're both January, so it doesn't actually distinguish. But in the general case, you can also get quite a bit of information of looking at the head noun of the noun phrase inside the prepositional phrase. And indeed, this kind of PP structure is essentially the one case in English where it seems like to do a really good job, you'd want to have three, kind of a joint probability between three lexical heads. So you had both you're deciding between announce in January versus rates in January, and you actually look at those lexical triples. Whereas the kind of lexicalized PCFG model everyone uses actually has lexical doubles. So they're often called bilexical probabilities. So you get announce in and in January, but you don't get the triple. But in nearly all other cases, having those bilexical probabilities seems to give you all the information you need. Okay, so this is the story of what people felt they'd learned in the 1990s from doing the work in that decade that made broad coverage statistical parsing seem successful. The basic story people told was that there was basic PCFG parsing with just the categories in the Penn tree bank, and that sort of worked, but it really didn't work very well in terms of getting good parsers. And so then what you did was you put lexicalization into your parsers, and that they worked great. This is Eugene Charniak at a 2000 workshop talk. To do better, it is necessary to condition probabilities on the actual words of the sentence. This makes the probabilities much tighter. And here's a good example of that. I'll show you another example in a minute. So one thing you can have in English is verb phrases that take two objects. So that's something like gave the man a book or told Fred the answer. So that's actually a distinctive property of Germanic languages. If you go to Romance languages like French, you can't get those two objects. But, it happens. How often does it happen? Not very often. But, well, what you can then find is if you actually know what the verb is, then you can, for some verbs, give as the kind of verb it happens with, and so that it's got a reasonable probability there, and for said, it basically doesn't happen. And so you get much tighter, more precise probabilities if you know what the verb is. And similarly, Michael Collins sort of makes the basic contrast between basic PCFG versus lexicalized PCFG. And so this gives this kind of a history of what happened with statistical parsing. There were basic PCFGs, and so this is the labeled, precision labeled recall F1 measure I mentioned before, even though he labeled it accuracy. Basic PCFGs around 73%. And then people started exploring how to build lexicalized PCFGs. So David Megerman, who was actually a Stanford CS PhD students' work was really a pioneering work on building lexicalized parsers. So it was really a very ugly model in the details of how it worked. And so it got to 84%. And then there was the work of Michael Collins and Eugene Charniak, who are essentially the two key people doing lexicalized statistical parsing in the 1990s, going to 85, 86, 86, 88, 89, so that the key jump appeared to be lexicalization, and then there was kind of gradual refinement of the models, and they got a little bit better. Now, as I explained last Monday when I talked about some of the work on accurate unlexicalized parsing, I mean, in retrospect, based on that work and some more work that I'll talk about today, I think that picture isn't quite right, because, well, what we showed is that we could get up to 86.3% by using a cleverly refined PCFG that just puts in some general syntactic context, but puts in no lexicalization based on head words that are content words whatsoever. And if you have that in mind, well then the gains from lexicalization start looking kind of small. We're actually better than these first two lexicalized parsers, and these ones are gaining sort of somewhere between 1 and 3%. And I'll come back to later talking a bit more about that. And we'll see that although lexicalization is useful and is clearly something you need in various circumstances, it hasn't yet been able to be turned into quite the magic ingredient that this early work made it look like it was. Right, so first of all, I want to present the parser that Charniak did in 1997. So Charniak's parser was essentially the simplest, most straightforward way in which you could build a PCFG, which was a lexicalized PCFG, and have it not completely uncomputable because of the enormous non-terminal space you get with lexicalization. Okay, and it's in the style of just a basic generative model. So this is the tree we want to generate, and we're going to generate it top down. Though the actual parsing, of course, he does is bottom up. Okay, so the way to think about this is to assume that we're at some point in the tree. So we've started generating a sentence headed by rows, which rewrites as a noun phrase and a verb phrase headed by rows. And we know that our left kid is going to be a noun phrase. And so to do the model for the Charniak parser, you sort of have a starting point here, and then we're going to do expansion down here. And they're essentially just two key probabilistic distributions they use to make each choice. So the first choice is to say, okay, here we have this noun phrase. This noun phrase is going to have to be headed by some word to be a lexicalized PCFG. So what we want to do is have a probability distribution over what word it's headed by. And so that's the one that's here as C. So what's the probability of a certain head word given the parent head word, the category that we're giving a head to, and the parent category? So the information we're using is the parent. It's going to be a dependent of rows. It's a noun phrase, and its parent category is a sentence. So you're using those three bits of information, and then you're choosing the head word by a probability distribution. And so you're getting a probability of it being profits versus some other word. Okay, so then at that point, we now have a lexicalized head again. And so the next question is to say, okay, well, we've now got this lexicalized category. How are you going to expand it? And so that's then here D. So D is saying, what's the probability of an expansion rule given a head, its category, and the parent category? So this time the information you're using is the category is a noun phrase headed by profits, which is under a sentence. So it's making use of this same, make use of the parent category to give a bit more information, but it's no longer making use of that. What are the probabilities of expanding in different ways? And so here the expansion that's been chosen is adjective, plural noun. And I've written here profits. The fact that profits is there is just deterministic, because we said here that profits is the head of the noun phrase. And so then for any particular expansion, it's deterministically given by rule as to what is going to be the head word of that expansion. So this expansion is JJNNS with this word being the head of it. So therefore we know that profits must be the head of this category. And so the thing that we still need to give a head word to is this guy over here. And at that point, we're precisely back to the picture over here of where we have something and we want to work out its head. And so we'd just start repeating over. Now, in this case here, I've already gone down to part of speech tags. And so we generate a head word and then we're done because it doesn't expand phrasally any further. But in the general case, it would. And so you can imagine that sort of expanding over here where there's more phrase structure left. But in general, you're just alternating. First of all, choose a head for a phrase, then work out how it expands. One of those categories will be the head, and we know it's head word. For the rest of them, choose head words for them, and then work out how they expand. Then for the expansions, work out the head. So you just keep on having those two distributions beat off against each other, heading down, and that gives you the probability distribution of the tree. Okay. And so this is a couple more charts of sort of data to give you some idea about how much information you can get where. So if you think about the lexicalization here, lexicalization comes in two places. One place it comes in is here, which is what's the probability of having a noun phrase headed by profits given that the verb that heads the sentence is rose. So those are the kind of probabilities that I used initially to motivate things, for examples like the prepositional phrase attachment, and they're referred to in the literature as bilexical probabilities because they involve two words, that you're conditioning one word on another word. Now, you're also conditioning it on other category stuff, but people kind of a lot of the time say, well, there's some other category stuff, but think of this mainly as a bilexical probability, basically because the space of words is so large that that's kind of the key thing to think about, whereas having one more, one less thing that you're conditioning on over here that's just a category like noun phrase doesn't matter so much. But then for this one here, when you're working out how to expand NP profits, you're not using rows. You don't have any facts about the heads down here yet. So there's only one lexical item that's being used on the conditioning side. So you're letting the expansion depend on what the head word is. And so those are then referred to as, unilexical, I guess you'd say, unilexical probabilities. There are only one word involved. And both of those are useful. So the key case where knowing the head word is very useful is this case of looking at the way verb phrases expand. So different verbs take distinctively different patterns of arguments, and there's just a lot of information in knowing what the verb is to knowing what patterns of arguments you'd expect it to take. And so here are some examples of this. So the four verbs that are being shown are come, take, think, want, and then these are various expansions of verb phrase and seeing how commonly they occur. So one possibility is that the verb phrase is just a verb. There's nothing else in the verb phrase. So that's a completely intransitive verbs. So that's something like I came, right? The came is just the verb phrase. And while that's fairly common for come, it's then rarer for some of these other verbs. I mean, you could think, wait, this shouldn't occur at all. I take. That sort of sounds a bit funny because normally take's thought of as a verb in which you have to take something. It's a transitive verb. If you kind of scratch your head, you might think, oh, maybe in chess or something you can say, I take, and there's no object involved there. But really, the place where these turn up is because these phrase structure trees aren't modeling the deeper kinds of dependencies that are going on in the sentence where things have been moved around. So if you have a sentence like, what did you take, where you're in a context of asking about a picnic or something, that in the phrase structure, the verb phrase will only have take left in it because the what that's the object has been moved out the front. Anyway, moving along, if you then consider other patterns, here's the transitive verb pattern, verb noun phrase. Take is basically a transitive verb, and so you see that 32% of expansions are here, whereas come basically isn't a transitive verb. You might wonder where that one comes from. I think where that one comes from is that there's this weird structure in English where various nouns are used as bare temporal modifiers. So if you have something like, I came last week, that last week is just a noun phrase. You know, you can say, I came on Tuesday, or caterpillars come in the spring, and you get a prepositional phrase expressing time. But you can also just use these bare temporal noun phrases in English, like last week. And so I presume that that's where that 1.1% is coming from. Think barely ever occurs. Want, like I want a new bicycle, you can get transitively, but you also get a lot of different things. And then you can go through the other patterns. And so some of them are quite stunning. So for think, the basic pattern for think is that you're putting an S-bar clause, which is a sentence with either an overt or no overt complement. You know, I think that is stupid, right? Or I think it's stupid. But either of those count as an S-bar complement. And that's actually basically just right there, 3/4 of the time, what you get for think. Whereas for another verb like I want, the want doesn't take an S-bar complement. At least it doesn't, except in very arcane forms of Shakespearean English. I want that you leave me now, or something like that, that it doesn't occur. And so there's kind of basically, you know, close to 3 orders of magnitude difference in the different expansions. Okay. But then you also get these bilexical probabilities. And here's an example of some bilexical probabilities. So the example I had before was prices rose, I think. This is showing it for prices fell. If you're using the Penn Tree Bank Wall Street Journal, which is a slightly biased corpus in terms of mainly covering financial news, if for either of the word rose or fell, if what pops into your head first for fell would be something like the child fell or something like that, that's not what you find in the Wall Street Journal. The things that rise and fall are prices and stocks and a few other words like that. And so they're actually just these incredibly strong lexical probabilities. So this one's showing that if the verb is fell and it's taking a noun plural subject, fully 1/7 of the time the head word of the noun phrase is prices. I mean, that's actually stunningly strong. But then you can look at what's the chance of finding prices with less information. If you just know it's a noun phrase subject that's a plural noun, there's a 5% chance it's prices. Wall Street Journal talks about prices a lot. If you just know that it's a noun phrase subject that's a plural noun, but you don't know the verb is past, it's 2.5%. If you don't know, if it's just a plural noun phrase, but you don't know where it is in the sentence, you're down to 1.3%. So that what you see is that you kind of get less precise estimates as you use less conditioning information. Okay, so the way that Charniak then built his model, because I mean the thing that should still have been in your head is, well, it's nice to write this, but how do we actually estimate this? Because they're all the same problems of estimating sparse probability distributions, because this is essentially kind of just like a bigram model made approximately 2,500 times sparser by also conditioning on a couple of categories. And so the way Charniak did that was he used linear interpolation, which you should remember well. And so this is the probability estimate that was used for the bilexical probabilities. So on the top one, it's everything, conditioned on everything maximum likelihood estimate. I'll mention that one in a minute. Then for this one, what you're doing is you're throwing away the parent head word, so that you're just conditioning on the current category and the parent category, so it's no longer bilexical at all. And then finally, you're also throwing away the parent category. And what you've got here is just a tagging probability, which is what is the probability of a category being headed by a particular word? What's the chance of a noun phrase being headed by prices, or what's the chance of a plural noun being prices? Okay, and the interpolation was done in a slightly clever way in which these weren't just constants, but they were done as functions based on how much evidence you had of different conditioning contexts. Okay, the one extra case in here was, because it seems an enormous gap going from conditioning on the parent head word to not actually conditioning on any words at all, Charniak tried to intersperse in here this extra case where he made semantic classes out of the parent head word. So this was done by distributional clustering algorithm. And so you'd condition on the distributional class of the parent head word rather than the actual individual parent head word. It turned out that doing that he got very little value out of. And in general, to this day, most people who build statistical parsers just haven't bothered to do that. It's an interesting research area still. On the one hand, it seems like surely you should be able to get good value from these kind of distributional classes, but on the other hand, in practice, it's often seemed very hard to get that kind of value. Okay, so here's an example then of how this smoothing works out in practice. So this is considering two cases. So this was the one that we had on the slide before of profits rows, and then here's the word corporate being a modifier of profits down in the bottom left corner of my slide. Okay, and so what we see in this example is that in the Wall Street Journal, I guess at the time, I think it's 1989 Wall Street Journal was when what the Penn Tree Bank was made out of. And I guess 1989 must have been a down year for stocks, because I showed you on the previous slide that if profits fell, that was 15% of what you saw for fell. It turns out that in the training data that people conventionally use for statistical parsers, this environment of profits rows as subject noun phrase doesn't occur at all. So you get 0 occurrences of it. So this most detailed estimate is 0, and then you're falling back to these effectively pretty imprecise estimates that, based on the class of rows, there's a 0.3% chance of it being profits. Then just based on it being a noun phrase and an S, it's 0.00. Well, there are these very small numbers, and it's very improbable. Here shows the opposite case of when the model does actually have something that is seen before as a bilexical probability. So in the Wall Street Journal, if the noun is profits, the modifier corporate is just really common. In particular, if you have this quadruple here of an adjective modifying a noun, and the noun phrase is headed by profits, basically a quarter of the time it's corporate profits. So you get this really strong bilexical probability where the chances of an adjective being corporate based on less conditioning information get a lot weaker. Okay, and so that's the kind of things that get smoothed together with these linear interpolations. And so on the one hand, obviously the linear interpolation is useful. On the other hand, there's something kind of very scary about how badly estimated statistically any of these quantities are, because it just sort of feels like it's really roll the dice randomness, that if you have something that's been seen as a bilexical probability, you're ending up, if you just imagine linearly interpolating these numbers using any reasonable weights, you're going to end up with a really high probability here, whereas if you're linearly interpolating these weights, no matter how you weight the 4 terms, clearly you're going to come up with something that's about 2 or 3 orders of magnitude smaller, which somehow seems quite a scary level of sort of bounciness in what comes out of things. And so that's actually a dominant issue when you think about statistical parsing, that on the one hand, I think one can rightfully tell the story that statistical parsing has just been really, really successful in delivering something that can reliably find pretty good parsers for sentences. But on the other hand, underneath that rosy story, there's this picture of building parsers based on this overly small resource which really just can't tell you the kind of information that you'd like to know in a lot of cases. So the biggest resource for parsing is the Penn Tree Bank. And so the Wall Street Journal Penn Tree Bank is 1 million words of Wall Street Journal. More recently, they also parsed some spoken material with switchboard corpus. So there's also 1 million words of switchboard material. But in practice, it's kind of hard to just combine the two together because there's so many differences with the spoken material. People say and a lot, among other things, that it's not really useful to just whack them together if what you want to do is parse sort of standard written text. So you've got about 1 million words of data. 1 million words has been a classic size of corpora, so that when the Brown corpus was made in the 60s that I mentioned earlier, it was also 1 million words in size. And as I think I mentioned then, at the time in the 1960s, they were talking about the phenomenally large size of the Brown corpus and how it'd be able to answer any question about the English language. But, you know, that just didn't prove to be the case. And you can kind of see that for the Penn Tree Bank. So here are just a couple of slides that talk about how little information you have for estimating things in the Penn Tree Bank. So you've hopefully seen in Programming Assignment 3 the kind of categories that we have for Penn Tree Bank parsing, which are the same as the ones you use. So we did the parsing this year over this biomedical corpus, which is smaller again. It's only about 100,000 words of parsed data, but it's using the same category set. And so as well as the standard noun phrase, verb phrase, etc. categories, the Penn Tree Bank distinguishes special categories for WH phrases, so the simplest of which are who and what, but can be complex phrases like what kind of a person would, steal money or something like that. Right, so what kind of a person is then a WHNP in the Penn Tree Bank. It's a WH phrase, it's a noun phrase. So if you look at the Penn Tree Bank, that the number of constituents, phrasal categories, is about the same as the number of words. There are about 1 million of those as well. But then if you ask the question, well, how many WH adjective phrases are there in the Penn Tree Bank? It turns out there are only 66 of those. And that doesn't sound so good for estimating probabilities of phrasal expansion. And then if you look a bit more carefully and you say, well, what are those 66 WH adjective phrases? It turns out that 60 of them are either how much or how many, because they're just the commonest two WH adjective phrases. How many books did you buy? But, you know, actually, there's an infinite space of WH adjective phrases, because you can take an adjective that can take complements, such as clever, original, incompetent, silly, stupid, any of those evaluative ones, ever positive or negative, and you can say, how clever, and then you can put a complement here as to what you're asking about, you know, so how good at math is he or something like that. You're in this infinite space of possible WH adjective phrases, and yet for this entire space, which includes this pattern and lots of other patterns, so another pattern you can have is for words like sure, they can take S-bar complements, so how sure that he will come are you, right? And so there are lots of different kinds of complex WH adjective phrases, and in the entire Penn Tree Bank, excluding how much and how many, you've seen only 6 of them, which just isn't much to go on to be building a model. Here's another example of that with the bilexical probabilities. The whole basis of lexicalized parsing is we'd like to use these bilexical probabilities. And the question is, well, can we use them, get value from them? And that's something I'll talk about more a bit later. But here are just some simple count statistics. So let's pick the most central, most evidence topic in the Wall Street Journal, which is what's happening to stocks. You know, that's just the most common thing to find data about. what do you find? Well, here are some counts for the stocks being the subject of things and what happens. So stocks plummeted occurs twice. I guess 1989 was a down year for the Wall Street Journal. Stocks stabilized occurs once. Stocks skyrocketed occurs no times. And stocks discussed occurs 0 times. And so, apart from the fact that, 2 isn't a big count, the central problem is that what you'd like to do is be able to tell these apart, that you'd like to know that stocks skyrocketed is a perfectly normal thing to say that you'd expect to be good, whereas stocks discussed shouldn't be okay, that just shouldn't be a possible sentence. Okay, and so that kind of suggests that you just can't get the data to do this very successfully out of the Penn tree bank because the data just isn't there, that the Penn tree bank is much, much too small. And an obvious avenue to go to fixing that is to say, well, there's a lot of other data out there, right? There are billions of words of data that are available as unsupervised data, and how can we get value from some of that to be improving parsers? And I think that's a problem that's now starting to see a little bit of success, but it's taken a long time to have it show some success. So there was early work, again, by Charniak in '97, in which he attempted to do precisely that, to improve his bilexical probabilities by using a lot more data, and essentially got no value out of it. But more recently, I should point out, McCloskey, who's a student of Charniak's at Brown, that they did a paper on self-training the Charniak parser. So what you were doing was essentially in a straightforward manner, train Charniak parser, go and parse a lot of million words of more text, and your hypothesis there is that although it'll mess up in various ways, a lot of the time it'll get the answer right anyway, and so therefore you'll be able to learn a lot more facts about bilexical probabilities, which will usually be right. Now, obviously there are dangers there because what you learn suffer from any biases that are already present in the parser. But they actually managed to get good results from self-training, and so effectively this was the first paper that showed successful results from augmenting the training data beyond the Penn tree bank to actually produce a parser that works significantly better. Until this paper, the only other results were, at best inconclusive and at worst negative, and the standard had essentially been that although it seems dumb and obviously too sparse, that everyone just trained off the Penn tree bank because it didn't work any better to do anything else. Okay. So something that it might be interesting to wonder is, well, how easy is it to do this Penn tree bank parsing once you lexicalize grammars? And the answer is that, this is slightly subtle. I think lots of people miss this the first time because it kind of looks like, well, we've still got these 3 categories, and it's just like before. Is the parsing problem any worse? And the answer is, yeah, the parsing problem is a lot worse. And it can be worse in 2 ways. One way is to say, okay, I'm just going to parse, and my space of non-terminals is then a pair of my old non-terminals and a word. And so then our complexity naively would be like it was before, g cubed times n cubed. But really, G is now of the size of the old grammar multiplied by the number of words. And so in terms of the old G that we used to use, this would be equivalent to G cubed times n to the 6th, because there'd be an extra factor of n hidden in each one of those. So that's really bad news if we're at n to the 6th parsing. If you want to be a little bit cleverer than that, you can essentially say, well, let me just use the A, B, and C, and let me remember where the 2 head words are inside phrases. Because it seems obviously wrong to have gone to n to the 6th, because really one side or the other here must be the head, and that head will then continue up to the higher phrase. And so if I just remember where those two heads are, then I've got another 2 factors of n there. And so then I have a running time of g cubed times n to the 5th. Okay, so that's a start. I've shaved off one n there. And, you know, if you just naively, if you sort of organize things with head words and naively run a lexicalized PCFG parser, you know, it's true. It's n to the 5th. So here's a bottom-up, exhaustive lexicalized parser. This is simple numbers for the length of the sentence. And here's time on a log scale. And look, that means it's linear, so it's polynomial time. And if you fit that, you've got an exponent here of 5.2. There's an interesting little fact there that I'm not going to get to in detail. A lot of the time, people are used to ON bounds being kind of worst-case bounds that you never get to in practice. It turns out that in general in parsing, if you just empirically plot your numbers and then work out the best fit exponent, it turns out that the best fit exponent is actually slightly higher than the ON bound. And you might wonder how that can be, since ON bounds are meant to be the sort of the worst case of what it can be. The reason it turns up is it really just turns up for low-level systems issues, so that as your thing gets bigger, that you are less successfully able to keep things inside your various L1, 2, 3 caches on your chip and things like that, and you've got more memory non-locality going on, you know, all that kind of system stuff that people try and ignore when they're doing AI kind of stuff. But it's a fairly reliable result that you repeatedly see. Okay, so that's sort of the worst case. I mean, if you look at the algorithms that Charniak and Collins used, I mean, as algorithms, they actually are ON to the 5th algorithms. They're nothing more than that. And so all of the work is then turned into how can we do various kinds of heuristic search to make this run rapidly in practice. And both of them did a lot of clever work in how to get their parsers to run efficiently in practice, both in terms of runtime and amount of memory needed. You can do better than ON to the 5th parsing. So there's been this interesting thread of work, principally by Jason Eisner and Giorgio Sutter, who've explored ways in which you can exploit some constraints in the class of grammars. So really, for all of the work that's been done in lexicalized parsing, you can actually reformulate in a clever way and turn it into an ON to the 4th problem. And if you put a fairly small constraint on how you go about doing things, you can actually get it back to ON cubed. I'm not going to present that now, but I will next Monday, when doing the final lecture, present essentially the same idea in the context of dependency parsing, and I'll show their algorithm at work there. Okay, so let me now for a few minutes give a kind of just a quick tour of what's happened in lexicalized probabilistic parsing after that Charniak 1997 model. So the Charniak model was very simple and straightforward. It's easy to explain, but in some, you know, it used grandparent nodes for conditioning, just like we're doing for our PCFGs for assignment 3, but it didn't do any of the other things that we encourage you guys doing, such as it didn't use any of these ideas of Markovization to break up rules. So as I discussed in lecture last week, that if you generate each child one at a time with no conditioning, that's bad because you don't have the conditioning information you need. But if you generate an entire PCFG rule jointly, well, then that induces unnecessary sparseness. So surely you can improve things by doing some in-between level of Markovization. So both Charniak and Collins and more recent parsers have done that. Okay, and so the Collins parser in particular is viewed as a Markov process that generates each rule. So that when you have a parent, the parent has a marked head for the lexicalization, and then there are other dependents to the right and other dependents to the left. And the way that the generation is done in the Collins model is you start from here, you first generate the first right dependent, then the second one, then the third one, and you keep on going in a language model-like way until you generate a stop probability saying stop generating dependence on this side. And then you go over here and you say, should I stop? If you say no, you then generate a first left dependent. Should I stop? If you say no, you generate a second left dependent, and you generate left dependence until you decide to stop. Okay. So this is the kind of picture of the Collins model. So you start with a parent which has both its head word and the head word's part of speech tag. This seems a subtle little detail, but it turned out in retrospect when Collins and Charniak were competing to try and outscore each other on parsers, that one of the little differences that turned out to be very important was that you can get quite a lot of value by not only head lexicalizing your grammar in terms of carrying around a head word, but also carrying around that head word's tag. And that's useful mainly because it gives you a useful extra level of back-off, that if you can't actually get information particularly from the word, you can at least use the word's part of speech tag. Okay, so then you know what the head, well, you then have to generate the head. You know what its tag and its word is going to be. You may have to generate its category if you've got a rule where the category of the head is still itself a non-terminal. And then after that, you start generating the children one at a time. And so the central thing here is in Collins's model, you generate them one at a time, but he has a model actually of subcategorization, which is which kinds of children you'd expect this head category given with a tag and word to generate. So this is kind of like this idea of if it's give versus think versus come, you'd expect different kinds of dependents to be being generated. Okay, and then, so firstly there's a model of subcategorization, and then there's kind of a sort of a general model of how much stuff you've generated so far. So Collins doesn't Markovize the grammar in a kind of an obvious way like we talked about for the PCFG, where you're sort of saying, well, I'll condition on the previously generated dependent or the previous two generated dependents. Collins does something rather more complex, but it's kind of was an interesting thing to try and do, which sort of relates to linguistic ideas. So his conditioning is, so when you're generating Li, you're not conditioning on Li minus 1 directly at all. You're conditioning on two things. You're conditioning on unsatisfied parts of the subcategorization frame. So the subcat frame would say maybe that this word likes to take a noun phrase and a prepositional phrase with certain probabilities. And if you've already seen the noun phrase, the unsatisfied part of the subcategorization frame would be a PP. And you're conditioning on a generalized distance measure. And this distance measure says some general remarks about what you've generated so far. So it records whether you've generated nothing or something so far. It records whether you've generated something that's headed by a verb so far, because that's sort of taken as an indicator that you've generated something kind of big and heavy. It records whether you've generated any punctuation so far, because if you've seen things like commas, that has a distinctive role. Okay. And so then, for doing it, when you're generating these non-terminals, you're effectively, again, doing these two probabilistic distributions, one of which doesn't have the words in it and one of which does. So first of all, there's a probability model of generating the next dependent, which is represented as a category and a head tag. And then there's the PMW, which is filling in, okay, what's the probability of that category and tag being a particular word here, John. So this second one is essentially exactly the same as Charniak's second probability, that you're filling in the lexical item that's going to be the head, whereas up here, you're doing this more articulated generation of the different dependents rather than simply having a simple PCFG rule. Okay, and Collins essentially used the same kind of ideas of combining different probability distributions, but in his model, he actually used a back-off model rather than using linear interpolation. So for generating the head word for the bilexical probabilities, that these were the back-off levels that were combined. And this was all kind of complex to look at. But here we are, we're conditioning the word, and these are all the things that we could condition it on. So this is what's the category, what's the tag. These are these kind of distance features. Have you seen a conjunction? Have you seen punctuation? You know what the parent category is. You know what the head word and tag of the parent category is. You know stuff about the subcategorization on the side. And there's one that I can't remember what it is, but you get the general idea. So then if you back off, what you do is the first back off is the only thing you throw away is conditioning on the head word. So you're generating the dependent word with all the other information but the head word. And then if this doesn't work, Collins immediately throws everything else away, and you're generating a word based on just knowing what the tag is. So this is what's the chance of being corporate given that it's an adjective. Okay. So another little bit about just more info on Collins' model. So Collins in 97 actually produced 3 models, which he named 1, 2, and 3, which the model I've presented so far is I guess closest to model 2, but model 1 had less conditioning, and then he had these progressively more complex models. So the kind of things he put in, actually put in some interesting bits of linguistics to try and improve things. So the distance measure, which favors close attachments, sensitive to punctuation. He put in certain state splits himself. So he distinguished full NPs with post modifiers versus base NPs that only had pre-modifiers like the large book or something like that, which also we got value from our unlexicalized parser. There's the coordination feature. Sentences with gap subjects, so that's like infinitives like I want to leave now, the to leave now is missing a subject, so they're distinguished from other sentences. There's the model of subcategorization that I've already vaguely mentioned. And then finally in model 3, he started trying to deal with that problem of the example I mentioned of what did John take. The take there looks like it's an intransitive verb with nothing else in the verb phrase. And so the idea here is, well, the fact that we're not accounting for things like those WH questions where something that is an argument of the verb has been taken outside of the verb phrase is really messing with our probabilities, because we say that take can be used in an intransitive verb phrase when really it can't. It's just that its object has been moved elsewhere. And so he implemented an idea that's been used in linguistics. I mean, this is essentially the idea that you still see in HPSG if you're someone that's done Ling 120, of having gaps or traces that are then threaded through the categories to keep track of displaced constituents. So this was kind of a nice linguistic idea to try and do. Actually, it never produced any positive value in terms of how well the model worked, just evaluated as a parsing model with this labeled precision, labeled recall. Now, you could reasonably think that if you actually want to do meaning recovery or even the kind of semantic role labeling where those long-distance dependencies are important to get right, that this stuff would come in useful. But if you're only wanting to get your labeled precision, labeled recall higher, he didn't succeed in that part working. But all the rest of this stuff that went into Model 2 was useful and shows, and I think it does start to show that some more careful linguistic modeling does give you some value. Okay, but something that's then been interested people and pursued quite a bit was, well, bilexical statistics of the kind that we claim to be central to these models, are they actually that important and useful for parsing at all? So one of the first pieces of work that addressed that was a piece of work by Dan Gilday, who was the same Dan Gilday who came up in the semantic role labeling. And so Dan Gilday kind of wrote his own attempt at replicating Collins's model, and he then said, well, suppose I just take away the bilexical probabilities. You know, that's an appealing thing to do statistically, because if you look at the probabilities in this model, that these kinds of models typically have, you know, a couple of million parameters, and really that a huge percentage of them are the bilexical probabilities because they're the maximally sparse ones. So you can take away a huge number of the parameters from the model by taking out the bilexical probabilities. Let me try that and see what happens. And so he did that, and he removed those bilexical probabilities that I showed you for PMW, and it turned out that the parsing accuracy only went down by 0.5%, very little. That result wasn't completely convincing because, for whatever reason, Dan Gilday's attempt to replicate Collins's parser wasn't actually as good as Collins's parser, that it sort of performed about 1.5% lower, so it was kind of a little bit unclear as to, well, for the other 1.5% that Collins is getting somehow, is that coming from lexicalization or is it not? But, you know, other evidence continued to mount that suggested, well, these bilexical probabilities unfortunately don't seem to be doing much. So David Chung and Dan Bickel then came up with the following result. So Dan Bickel worked on very closely emulating the Collins parser in a re-implementation, and successfully did that to get the same kind of results that Collins got. And they tried out an experiment of, well, rather than using this idea of the head of a phrase, of nouns being the head of noun phrases and verbs being the head of verb phrases, what if I just always choose the leftmost word as the head of the rewrite? Don't make use of any linguistic information. And so it sort of seems like if you do that, a lot of the time your bilexical probabilities kind of should be crazy because they'll just be between two weird words. And, well, it turned out that you could do that, and again it seemed to make pretty little difference. So I guess here you're losing a bit more than 1%, So you're only losing 1% and a bit from choosing kind of crazy weird head words. And so here's then more work from Dan Bickel so this was sort of then some later work when he'd done this full replication of the Collins parsing model. And so here's the full model, which is working very nicely like the Collins model. And, well, you could take away the bilexical probabilities altogether again. And now it's looking again basically essentially like Dan Gilday's results, that you're only losing about 0.5% by taking out the bilexical probabilities. And so that makes it look like the bilexical probabilities are almost useless. And so that was something that intrigued Dan Bickel, and he went on to work on quite a bit further. And so one of the things that he looked at was, well, when I'm running my parser, it's all the time looking up probabilities. And so it's saying, okay, I'm considering putting together this noun phrase with this verb, this sentence headed by a verb phrase. Let's look up the probability of that using my bilexical probabilities. And so let me just instrument my parser and look at when it asks those kind of questions as to how does it actually answer them. To what extent does it back off in that 3-level back off that I showed you before. And, well, what he found was that, well, actually, you know, it's answering the question with a bilexical probability only 1.5% of the time. It's using the rich everything but bilexical probabilities to answer about 11% of the time. And 87% of the time is actually just backing off and is using the estimate of the probability of a word given the tag. And none of the other conditioning is in there. Okay, so that makes it look like the bilexical probabilities aren't really playing much of a role because of data sparseness, that most of the time you just don't have any counts for the bilexical probabilities, and so you have to back off. But you could object to that result and say, well, you know, if you turn on exhaustive dumping of what one of these parsers are doing, most of the time they're pursuing completely crazy, weird, horrible parsers that look nothing like a possible sentence of English, that's just kind of what these parsers do. If you explore their search space, you might have noticed that with your parsers. So maybe that's a stupid question to ask, because, yeah, most of the time it's trying to pursue some really crazy theory, and so, yes, you have no bilexical information on that, but that's for good reason, because it's trying to pursue some crazy theory that would never turn up. And so, therefore, what we really want to do is look at the parsers that are actually the correct parse, because maybe what happens is that when it's pursuing a correct parse path, that most of the time it can use bilexical information, and it's only when it's doing crazy theories that it can't. And so that turns out to be the case. So if you measure that, what's the percentage of the time that bilexical statistics were available on decisions that were made in the parse that was the parse chosen by the parser? It turns out that bilexical probabilities were used almost 30% of the time, so about 1 time in 3. So that makes it look like, okay, bilexical probabilities are actually used a lot in the correct parse paths. But that then leaves still a remaining question, which is, well, okay, if they're used a lot in correct parse paths, why is it that if you turn them off altogether, you're only losing about 0.5%? And so Dan Bickel did some further data analysis on that, and it turns out that a lot of the time, the lexicalized probabilities just aren't actually very different to the unlexicalized probabilities. And so this is essentially recreating the kind of idea that underlay the accurate unlexicalized parsing investigation, that a lot of the time you can predict what's good or not based on categories, and knowing the lexical item isn't significantly altering those probability distributions, that it's really only in a minority of cases, that's cases like certain of these prepositional phrase attachments, where there actually is information that really does markedly affect what decisions that you should be choosing. And so the fact is at the moment that you've got this intersection of there are only a limited number of spaces where that information is useful, and then there's only a limited percentage of those where your statistics are available to actually do a good job of it. And the intersection of those two things leave you with a small space where you help, and that's what gives you about 0.5%. And, well, the first half of that I think is just a fact of nature, but the second half of it is the part about your very sparse data, and that part you can at least help to improve. And that's where this question about how can you actually get better estimates of bilexical probabilities I think is still a good research area. Okay, so then very quickly the rest of lexicalized statistical parsing up to the current day. So the generative lexicalized PCFG that was kind of the mainstay as the one that worked best and a lot of people used for a number of years was a later version that Charniak did in 2000, and he published it under a title of a maximum entropy inspired statistical parser, which was sort of really misleading and confusing because it might have made you think that it had something to do with maximum entropy. But you've got to pay attention to the inspired word. I mean, really it was still just a generative parser, and the supposed inspiration was he used some kind of clever ideas about how to do the smoothing of the probabilities, where you're looking at ratios of probabilities between something that has conditioning and doesn't have conditioning, and somehow he's thought of that as sort of inspired by having looked at maximum entropy models. And then it picked up other details. So I've already mentioned the conditioning also on the tags, Markovizing rules like Collins did, and that got up to about 90% labeled precision and labeled recall. Much more recently than that, another interesting bit of work by Slav Petrov and Dan Klein was that they essentially continued along the line of the accurate unlexicalized parsing in saying, well, maybe we can get a long way by just having a limited number of categories represented in phrasal trees and not going the whole route of lexicalization. But suppose we kind of freed up and got clever about how we did those categories. So rather than hand producing a grammar by doing careful category splits, suppose instead we say that our backbone is Penn Treebank categories, but we're going to expand this space by learning latent categories. So each phrasal category is a combination of the original Penn Treebank category plus some latent variable which we're going to learn from data. And so this was done essentially by EM learning. In practice, they did some clever stuff, which you'd have to go and read the paper if you want to learn the details of. I'm not going to do it here. And the essential part that's cleverly done is that they use this category split merge procedure so that you're attempting splits of categories, you're then evaluating whether the split proved to be useful, and if not, then you're backing it back out again. And at any rate, the way they did that proved to work extremely well, whereas there'd actually been someone else a year or two earlier who had naively done the, okay, let's put a latent variable here and just do basic EM over a latent variable, and that basically didn't work very well at all, whereas the kind of clever splitting procedure gave a lot of value. Okay, and so in particular, from the clever splitting procedure, you're only splitting the categories that benefit from splitting. So this is showing you in their grammar how many subcategories they produce for different Penn Treebank categories. And so for the ones that don't have much variation in internal structure, so here you have WH adjective phrase and WH adj phrase and S bar Q and conjunction phrase, that they're not split at all, they're just still a single category, or they're split into two subcategories. Whereas over on this side, for categories like noun phrase, verb phrase, and prepositional phrase, they're splitting them into somewhere around 30 subcategories. They also split the parts of speech. And so this is showing you some of the ways in which the parts of speech are being split. And so a crucial thing to note at this point is that this isn't anymore an unlexicalized grammar in the sense of the original unlexicalized parsing work, where the idea is you didn't really want to put in specific information about words. Here you clearly have specific information about words. So here you essentially have word classes. So you have a word class of, here are family names, here's two word classes that are locations. These are kind of first words of two-word locations, and these ones are second words of two-word locations. Here are months, etc., like this. So you effectively have this grammar that's done over word classes. The interesting thing is that whereas word classes didn't seem to work very well in that Charniak 97 work, word classes for these guys seem to work very well indeed. And I'm not quite sure what the difference is from that. Anyway, here are some final parsing results. So here's accurate unlexicalized parser again. This was what I just mentioned, that if you just sort of simply said, okay, for each category, let's put in a latent variable and assume that you have 16 subclasses of that category, well, it sort of works, and you could say this is a little bit better, and it was done automatically rather than hand split categories, but it kind of doesn't really work much better. Here's the Charniak 2000 model. The interesting thing is that the Petrov and Klein work tidily beats the Charniak 2000 model. And so again, this is this result that lexicalization is getting some value, but the value you're getting still seems to be pretty limited, actually, because this does have this word class information, and that word class information is useful, but it's clearly got a lot less of that than a real lexicalization. Because if you remember back, categories, well, maybe I didn't say, the way their algorithm was done, that categories could be split into, at most, 64 subcategories. That was the sort of limit of splitting. And in practice, most categories had at most around 30 subclasses. So they're fairly crude. Although they're semantic classes, they're fairly crude semantic classes. They're not very fine-grained, and yet this works extremely well. But Charniak hasn't stopped working on parsing. So the most recent, this is kind of effectively at the moment, the state-of-the-art best parsing numbers. So this is then taking Charniak's 2000 parser and then putting a discriminative re-ranker onto it, and I'll say a little bit about that next time. And so that then gets the numbers up to around 92%, and that's sort of the state-of-the-art for parsing, which is in some sense, given the difficulty of the task, pretty good, I reckon. Many people believed in the late 90s that sort of numbers around here, 86, 87, was where you could get to given 1 million words of tree bank data and, talking about data sparseness as I've been talking about. But I mean, actually, getting from here to there, that you're getting kind of fairly close to getting a 50% error reduction. And so, at some point it seems like you're just not going to be able to get further without having more data available. But, this piece of work here is again in the space of the only training data that's used is the 1 million words of Penn tree bank data, and there isn't any other information outside of that. Okay. So then I wanted to go on and say a little bit about how do people go about parsing with search algorithms. I'm almost out of time, and so I'm not really going to get to do very much of that, but maybe I'll just spend a couple of minutes and sort of say a bit about the general problem setting, and then at the start of the next time, mention a couple of ways of doing it. Okay, so in general, when we're parsing, fundamentally what we have is a search problem, right? So we have a grammar, we have a sentence, and we want to search to find something. The things that we could want to find is that we can just want to find the best parse for sentences. So that's what you're doing in the assignment, and is the most common task. But there are other tasks we could have. You could want to find a bunch of reasonably good parsers for a sentence. This is often useful if you want to do further processing. So, for example, some of the semantic role labeling work takes a number of good parsers and tries to generate semantic roles based on that, and precisely because that gives you greater robustness, because you're not putting all of your eggs in one parse basket, that helps a bit. Or another thing you might want to do is find the total probability of all parsers licensed by the grammar. So this is both what you want if you want to use a parser as a language model for something like speech recognition or any other task like machine translation. It also turns out to be that this is the problem that you need to solve if you're going to build discriminative parsers. And so in general, there's then a space of ways that you can do things. So we've looked only at CKY for finding the best parse, and that's what you do for the assignment. You can extend that to all of these problems. So you can extend CKY style algorithms to do k-best parsing. There's a very naive way to do it, which you can probably think up in your heads, which is you think, okay, each cell in my chart, instead of storing the best thing there, let me just store the k-best things and then just run the algorithm combining all of these k-best things. And you can do that, and that works correctly. But it has a high space and time cost, because if you do that, you're then combining k things with k things in each cell, and so you've got an extra factor of k squared. And that means that if you'd like to get 50 best parsers, as a number of people sometimes use, that means your parser is 2,500 times slower than it was when you were just getting one best, which is kind of unpleasant. It turns out that you can work out a much cleverer algorithm to find things than that, and the central idea of that is you kind of do deltas. That you know that a second best parse is mainly going to be like a best parse apart from different in one place. And if you want to know about that, you have to go off and read this paper. But you can do a clever ways of decoding k-best parsers. And so you can also then use the similar kind of chart and CKY idea to work out total probability of all parsers, and that then gets referred to as the inside algorithm. And this is then effectively, where you had the max in the CKY algorithm, you sum the probability of all analyses that you find, and you put that in the cell instead, and then you have the total probability of a cell. Okay, so CKY is a good thing to know about. But you know, if you're interested in finding just best parsers, which is what most of the time we're doing a lot of the time, there are a bunch of other ways that you can do it. You can use beam search again that I mentioned in the MT case, but you can also use ideas of agenda-based parsing, which is effectively ways of exploring different search strategies so that you're not doing a lot of work that's never going to turn up in the final parse. And so next time I'll say a little bit about how agenda-based parsing works. But that's it for today, except that Paul and Vijun have the programming assignment 2s to give back.